Hey everybody, welcome back to our series on Vertex Operator Algebras. Today we're tying off some loose ends in our story of Heisenberg modules. Notably, we'll show that the central charge of the Virasoro operators on our family of modules will amount to the dimension of the underlying abelian Lie algebra. So let's start with a quick review of these two modules. Recall that h hat z is the commutator subalgebra of the extended affine Lie algebra over the abelian Lie algebra H. This all means that we have adjoined the degree derivation of the Laurent polynomials, D. The natural modules on these algebras are the symmetric algebra of their negatively graded subalgebra. Just to drill this point home, we point out that h hat z is isomorphic to those elements in the affine algebra with non-zero powers of t. So the subspace of homogeneous degree 0 is restricted to the one-dimensional central extension. We can reverse engineer the extended affine Lie algebra by re-appending the degree derivation as the degree operator and then taking the direct product with h. Thus, the symmetric algebra of h hat z minus can be made into a virgulia h module by demanding two things. First, let D act as the degree operator. Second, we can explicitly factor out a one-dimensional vacuum with a basis element, say v sub alpha, associated to some chosen distinguished element of h, say alpha. The z plus 1/2 case has an analogous story, but of course it's a virgulia h minus 1 module. As a virgulia h module, m sub 0 is basically the same as the symmetric algebra over h hat z minus. M sub alpha has an explicit vacuum vector v sub alpha. And here we're going to update the information on that one form lambda. Lambda of c still equals 1, but now lambda of h, for h in the central subalgebra, h, involves a projection of h against alpha. And lambda d now becomes the degree of the relevant vector, for the particular case of the vacuum vector, v sub alpha. All is as you'd expect, although the degree of the vacuum vector, v sub alpha, is a choice that we're going to punt until we have to define it. The virgulia h of minus 1 module, m1/2, is essentially the same as the symmetric algebra of h hat minus z plus 1/2. Recall that the Virasoro algebra of operators on these m modules has the typical form. Our claim is now that c, this normalization, is given by the dimension of the underlying abelian Lie algebra H. Proof. Recall that the commutator of L of m and L of minus m equals 2mL0 plus the central term represented by gamma. Since m has a contravariant form defined in section 18, and using whatever the vacuum vector is for the given module, say v sub 0, we have that gamma of m and minus n is equal to the bilinear product of the commutator of L m with L minus m minus 2mL0. For our purposes, fix m at some value greater than 0. So we now compute. First, observe that because m is greater than 0, L of m acting on v vanishes because L of m is positively graded, and therefore the commutator of L of m with L of minus m in this product reduces to its simple product. That's just the definition of the vacuum. Next up, consider the L of 0 term for which we just insert the previously defined operator. Again, since h of k on v sub 0 vanishes, for k positive, we end up with two terms, those proportional to h sub I of 0, and the remainder term, 2 beta sub 0 dim h. Note that h squared of 0 amounts to the dimension of h times the inner product of alpha with alpha on m alpha. For all other modules, it vanishes. Similarly, beta sub 0 equals dim h over 16 on m1/2, and for all other modules, it vanishes. So finally, we essentially have the product of L of minus m on v with itself, with m not equal to 0. To that end, we first compute L of minus m using the involution omega. This affords a representation in terms of two finite products of h sub I pairs, because h of m operators commute with one another when their degrees don't add to 0. This amounts to a sum over indices k and l. This gives the overall central term gamma m minus m equals 1/2 dim h times the finite sum over k minus the correction bit. Recall that for m alpha, the h squared sub 0 term is non-zero, but it is cancelled by the would-be n terms in the sum with k equal to 0 and k equal to m. So, for the modules m0 and m alpha, the central term is given by, which you can demonstrate, of course, by induction. Curiously, for m sub 1/2, the central term is the same. So, normalized by 1/12, the central charge is fixed to be the dimension of h. And we're done. Another loose end to tie up here involves the degree of the alpha vacuum. To that end, consider the L of 0 operator on the vacuum vector of m sub 0 and m sub 1/2. For m sub 0, the degree of the vacuum vector is 0. Notice that L of 0 acting on L of m on v sub 0 amounts to the value minus m. Since the degree of Lm is m, we see that L0 effectively amounts to minus the degree derivation. So what's the case then for m sub alpha? Well, L of 0 on v alpha equals half of the inner product of alpha with itself. So to keep with this pattern, we'll define the degree of v sub alpha to be minus 1/2 alpha with alpha. Recall also that the Virasoro Algebra's central term, while unique, has two convention-dependent parameters, alpha and beta, and of course we can shift beta all the way to 0 if we like by shifting L0. If we shift L0 by, say, minus c over 24, we see that the linear central term vanishes, and we're left with c m cubed over 12. So it's a bit of a shocking move, but it will be motivated. Let's actually define this shifted L0 as minus the degree operator. This is just a grading shift on each m by dim h over 24. So, up to a minus sign, we'll call the unshifted degrees weights, and fill out the table with the data that we'll need in future studies. Finally, we'll close with a discussion relating these shifts with all these factors of 1/12 flying around. Recall that the 0th Virasoro operator L of 0 has to be augmented from the naive L of 0 to ensure that the operator is well defined. We had to essentially pick an ordering and a route through the integers. Indeed, for negative k, we essentially flipped the order of the operators. Now, the commutator of h of k with h of minus k is actually equal to that integer k. So, essentially the difference between the well-defined L of 0 and the naive but unfortunately not well-defined L of 0 amounts to the sum over all positive integers k, or k plus 1/2, depending on your module. That sum essentially amounts to a particular, though unique, analytically continued value of the Riemann zeta function at minus 1. In other words, that factor of minus 1/12 arises from L of 0's operator redefinition. Amusingly, this exactly accounts for the operator shift, dim h over 24, in all of our modules m. And we're done for today. Next time, we'll discuss the concept of graded dimension and reveal a mystery about this shift associated to these modules.